Yes?
Yes, sir.
Yeah. So now let us solve problem number 6 and problem number 7. Okay. Then after I'll be giving you these all whatever the script we have written. Okay, code we have written for all these problems, 7 problems. I'll be giving you a Word document with all the code syntax. Okay, then yourself you can practice once. By that way, with this tutorial itself, you will be having very nice idea about how to run EES and how to write a small codes. Okay, that knowledge is sufficient. Anyhow, in further classes, in further tutorials. Okay, so we will be practicing more. That will be giving you further more idea. Okay. That way, you will be solving both conventional method as well as EES method. Okay, so whatever the question will be asking you to solve, either in conventional method or otherwise in particular ES method, we no need to worry. Okay, whatever the question, we no need to worry because both ways we are practicing. Okay, so now let us see problem number 6. What is the problem number 6? You have seen it very well. Yes. So what it is saying? So we have practiced it also. Finally, what you need to find out? Heat transfer we have to find out like this. Yes. Heat transfer we have to find out. Yeah. So what it is telling you? So can anybody tell me? So what shall I write? Step by step. Hmm? Hello. Yeah, try yourself. No problem. Keep telling I'll be writing. Yeah, it's like yesterday only, nothing. Huh? It's like yesterday only, nothing more. Yeah. Practice. Anyone can suggest, right? This is just practice class only. Hmm? Sorry, by mistake I clicked upon that. So I went sign out from this. Okay. So yeah. So please tell me what shall we do for problem number 6? Because you have already practiced with this problem, right? The conventional method you have practiced. Yeah, even this tutorial also I have shared with you. Hmm? Then what shall we do? Tell me, step by step. T1, what they have given? T1 is minus 40, is it? And then there, this is the point, right? One point is this. Here, x equal to 1, is it? So, x1 equal to 1. Yeah. Then after what is given? T2 point also given here. T2 and T2 is given. Yeah, T2 given. And P2 also given. Yes. And then P2. P2 is how much? Uh, 6 bar. So we need to put in terms of kilopascal, 600. Okay. So now we need to find out what is the pressure at 1. Yes, at this location. What is the pressure we have to find out. Then what can we write the code? You know very well about it. This. Can anyone suggest me? Pressure. Yes. And then what is the fluid over here? This is the propane. Yes, sir. This is propane in the problem. So we will have to write simply propane. Okay, fine. Then where we are finding out its pressure at this point. Okay, what are the values we know over here? Two independent parameters. We know temperature T1 and its dryness fraction 1 we know. Okay, so T equal to T1, X equal to X1. Anyhow, we can use 1 also simply. Okay, so how much is that? Let me run and see. Okay, this is the run button. Okay, so how much is the pressure? 1.11 bar. Yeah, this is only that. Yes, 1.11 bar. We have calculated that. Fine. Then what we need to do? We need to find out specific volume over here. Yeah, and then how to find out the specific volume of 1 equal to, that is simply volume only, right? Volume. So again, fluid is propane. Okay, and then is the same. Okay. Okay, let me run. What are we getting over here? This is its specific volume is this much. Is it? Its specific volume is this much. Is it true? Yeah. Okay. It is here. Okay. 0.3798. Okay. So then what we need to do next? We need to do specific volume 2. Okay. Where in this location. Yes. In this location we have to calculate. However, that is not very difficult. The same formula. Okay. Don't worry. These all code I will be giving you by pasting in a Word document. Okay. So that way you can again practice yourself. So this is volume. Then what can we give over here? T2. Okay. What we know more? T2 we know. Yes. Yes. Let me run now then. Yeah. So this is the specific volume at this particular location. Yes. Let us check is this matching with the data or not. Yeah. See this. Yes. 0.1045. Okay. This is also matching. Then what we need to find out here actually the problem was Q, heat transfer Q you have to calculate. Okay, so heat transfer Q you have to calculate means you need to calculate work as well as internal energy. Okay, what is the formula of work? What is the process given over here? If you read it, PV power N equal to constant. Yes, PV power N equal to constant. That means any polytropic process, you need to calculate N value. Here we don't know N value over here. Okay. How we have calculated over here, I think you remember this question we have practiced very well. Okay. By this process. Yes. By this process, we will be finding out. Okay. Now we know everything. P1 we have calculated here. Okay. And then P2 given in the problem. And V1, V2 just now we have calculated over here. Then what would be N? N would be simply a formula, nothing more. Yes, ln E2 divided by E1. Okay. Ln V1 by V2. So specific volume integrated by V. Okay, then let me run. Yeah, so what it is giving n value, n equal to 1.308. Yes, it is matching over here. Yeah, then by following this method, the next what can you do? You can use this formula. Okay, for case of polytropic process, we have practiced this thing, this derivation also. Yes, P2 V2 minus P1 V1 by 1 minus N. Okay, now P2 you know, V2 you know, P1 you know, V1 you know, N just now we have calculated that way. You can get your work. Okay, this is simply algebraic calculation, nothing more. Okay, so that you can write over here. Okay, then you can calculate internal energy. Okay, internal energy you can calculate. So internal energy, what is this? You know, U1 equal to int energy. Okay, so at this point, let us see. Yes, propane. Okay, then calculate and see. Yeah, yeah, this thing. Okay, this thing. But however, you need this is for kilojoule per kg. Yeah, so then you need to multiply with mass and all. Okay, so then you will be specific volume and mass. Okay, then you will come to know. Like this way, you can conduct whatever rest of this calculation like this. Okay, this is about problem number 6. Okay, now problem number 7. That day we have practiced very well.
Sir,
That
why
is,
we write here the Q equal to del U plus W? It is minus W, na?
what is that?
Sir, means internal energy equals to Q plus W. So Q equals to U minus W.
U equal to, yeah, Q minus W. U equal to Q minus W, right? First law of thermodynamics.
So we write it
Delta
Q.
U equal to Q minus W. Yes. Delta U equal to Q minus W, not W minus Q. Okay.
Okay, fine, sir. Fine.
Yeah. So this is about our problem number 6. Now problem number 7, as we have seen, okay, that is cycle. Yeah. So we have this for this kind of cycle. 3 processes have been given over here. Process 1, constant volume process. Process 2, 3, constant temperature process. Process 3, 1, constant pressure process. Okay. These are all 3 processes together reflecting like this. Okay. All 3 processes are reflecting like this. Okay. Now what you need to calculate over here, they have asked you to calculate what is the cycle. This is power cycle or refrigeration cycle. Okay, so network output, if it is positive, then it would be power cycle that we know. Okay, this we have practiced. So now for this formula, whatever this for this particular problem, let us write the code. What is the working substance over here? That is ammonia over here. Okay, that is ammonia. Then what is the data given? Give me 1 minute. Yeah, yeah, Manibhushan, I am in thermodynamics class. You know that, right? Okay, come after 11 o'clock. Okay. So what is the data given here? Mass equal to 2 kg. Yes. So whatever suppose if you want to write some comment, you can simply write in inverted commas. Okay. So that will not be considering as the code. Okay. Besides this, you can give some space and you can write whatever the comment you want that in inverted commas. Right? Yeah. So then what P1, how much P1 has given equal to how much it was? Yeah, 10 bar. Okay. So this is 1000 kilopascal. Yes. Then what they have given more x1 equal to 6. Is it? Equal to not 6.6. Okay. Then uh, here they have mentioned that it is reaching to saturated vapor. Okay, in the process 1, 2. That's what x2 equal to 1.0. Fine. Then what next? In the process 2, since this is a constant temperature, and they have given Q23. Okay, Q23 equal to 228. Okay, anyhow, that is in the kilojoules because we set our units like that only. Okay. Okay. Then what we need to do now? The specific volume at 1. Okay, that we don't know. So we are calculating specific volume 1 equal to. Okay, so we know all the properties over there, right? So volume, since the fluid is ammonia, and then that is P equal to P1. Okay, and then the initial stage was, so here, okay, this was some mixer stage. Yes, it was some mixer stage. At x equal to x1. Okay, then let us see. Let us calculate and see. Yeah. So what is the specific volume we got over there? 0.07776. Is it matching with this anywhere? Yeah, here. Okay, it is matching with this. Okay, in case of your conventional method, what you have to do? This value would not be available directly in our data book. Okay, you have to calculate or you have to find out from your data table of ammonia this liquid specific volume, saturated liquid specific volume, and saturated vapor specific volume. Then you have to use this particular formula. Okay, then you will be calculating this particular specific volume at 0.1. Okay, at 0.1. Since everything is given over here, this is the software, so it is directly calculating this value. You no need to use that particular formula. Okay, then so there what you need to find out, all three steps means all three processes, we have to calculate our work. Okay, our work we have to calculate. Then all summation of three works, that is only we have done over here. Okay, so we have calculated W123. Okay, so W112, W23, W31. Then all works we have calculated are added over here. Then that has given you net positive. Okay, that means this is the power cycle we have concluded. Now the same thing we are going to do over here. Okay, then what are we doing over here? Then U1 internal energy at 0.1 equal to int energy, yes, and then ammonia. Yeah, then you know that P equal to P1 comma x equal to 0.6. Okay, then run it. Let us see. Yeah. Okay, this is the internal energy. Okay, is this matching with this? With this internal energy? Yeah, obviously this is matching. Yeah, the somewhere small things would be there here and there. Okay, whatever we have interpolated over here and whatever it is taking exact value, obviously the difference would be there all the time. Okay, this is the internal energy at point 1. Now state 2 is telling about what? State 2 is saturated vapor state. Okay, here pressure would be increasing. Okay, so then that we will be calculating. Okay. Then here specific volume, what is it is saying? Specific volume 1 equal to specific volume 2. So we are equalizing specific volume 1 equal to specific volume 2. Okay, then this part is over. Then what are we doing over here? We are calculating P2. Yes, pressure. Okay, then ammonia. Okay, then what are the two independent parameters we know? So one we know, specific volume we know. The next one, its dryness fraction we know. So V equal to specific volume 1 or 2 anyhow. Okay. Then x equal to 1. Let me run. Yeah. So how much is the P2? P2 is 1662 kilopascal. That means 16.62 bar. Is it? Let me check. Maybe it was not required over here. That's what we have not calculated over here. Okay. So it was not required anywhere. So that's what we have not calculated anyhow. No problem. Okay. Anyhow, we have calculated here for our purpose. Let us see that. Then U2 you need to calculate. U2 equal to int energy again ammonia. Ammonia. Ammonia equal to 2. Okay. Fine. Then yeah. So what is the internal energy over here? 1361. Yes. So is this matching? U2. Where this U2? Yeah, U2. Okay. This is giving you 1341. Okay, here and there it is okay, fine. Okay. Then here from this data, which data? From this data we have calculated temperature also. Okay, from this table A13. Now let us calculate temperature also over here. Because next process 2-3. Okay. Process 2-3 is isothermal process. That means P1 V1 equal to P2 V2. Yes. So now let us see. Now let me calculate P2. Okay. So let me run again. Okay. So what is the temperature we have obtained over here? 42.41. Yeah. Here it is 42.52. Okay. Here and there it is okay. Fine. Done. Okay. And then now the process itself is saying P3 equal to P1, where see this process. Okay. This is isothermal process. Okay, but from 2 to 3 when it is reaching, the P3 equal to P1 it is saying. Okay. Now all the points we are calculating actually. Whatever the data is required, internal energy, pressure, temperature, specific volumes, at all 3 points we are calculating. Then after we can calculate whatever the work output. Okay. So now what are we doing over here? P3 we are equalizing to 1. Okay. Then that is done. And since the process is isothermal process, okay, T3 equal to T1. Okay. Then now we need to calculate U3. U3 equal to in energy ammonia. Okay. And then P equal to P3, comma T equal to 3. Then how much it is giving us? What is this? There are 14 equations. P3 is there. Then T3 but 15 variables. T3 defined, right? T3 defined. And the problem is U3 energy. So what could be the problem here? Okay. T2, yeah, this was a mistake actually. See, T2 equal to T3. This is the process, isothermal process, right? Even T1 we have not defined anywhere. Yes? T1 we have not defined anywhere. T1 is unknown. Is it? Yeah, this is the problem. Yes. Okay. Now, yeah, fine. So what is given? U3. U3 1395. Is it? Let me see. U3, yeah, 1374, a little higher side. Okay. Then fine, no problem. Then what we need to find out next? So, specific volume, we need to find out. Is it? So then that is volume here. Is it? Then equal to P3. Sorry. Then run it. Let us see. Okay, so it's a specific volume also given over here. V3 is 0.14027, right? Yes, we have obtained this. Okay, we have obtained this. Fine. Then now let us go to the calculations part. Okay, and then now in the process 1, 2. Okay, this is the process 1, 2. This is what process is that? Constant volume process, is it? Constant volume process. If it is the constant volume process, then work done equal to 0. Yeah, work done equal to 0. Then what is that? Internal energy is equal to Q. Yes, internal energy equal to Q. So that way, here we have calculated Q. But anyhow, now we are just seeing whether cycle is power cycle or not. Okay. Anyhow, this also let us do. It will not take any long time. Anyhow, we have defined everything, right? Okay. This is Q1, 2. Okay. This is Q1, 2. So here internal energy equal to heat transfer. Work is 0 because this is the constant volume. So what it is giving you? Q1, 2. Okay. Q1, 2 is giving you 844. Is it? Yeah, here it is 844. Okay. Then what we need to do? W23. Yeah. W23 equal to what it would be? Q23. Yes. Minus mass multiplying U3 minus U1. Is it? Fine. Yeah. Let me run. What is Q23? Why it is giving the negative value? U3 minus, sorry, this is U2, right? Yeah, because this is process 2, 3. Yeah. Yeah, 160.9. Is it matching? Yeah, it is matching. Yes. Now process 3.1. Process 3.1 is this process. What is this process? Constant pressure process. Yeah. In case of constant pressure process, what is the work? So P delta V multiplying by mass. Okay. Yes. Let us
Sir, I
see
have a
that
doubt.
also. Yeah, please, please. Your voice is low, so can you please talk loud?
Yes, sir. Sir,
Yeah.
in process 2, 3, there will be is a constant temperature process, है ना?
Yeah.
So at constant temperature, internal energy does not change, na? But why should this U2 not equal to U3?
U2 equal to?
Means at constant, in a constant temperature process, internal energy change in internal energy becomes 0.
No, why it is? Temperature we are maintaining constant. Then we will be changing pressure conditions and according to the volume conditions. Check your equation in the first class. Okay, that slides, then you can understand.
As sir, we learn the internal energy equal to mCV del T.
Mm.
Here, sir,
Okay.
temperature change will be 0. So why should we saw the change in internal energy here?
Internal energy change. Yeah, that is correct. But still here, slight change is there in between U3 and U2. That is 1350. So 1300. What we have seen over there? Yeah, 1374 and 1341. Okay. So from the property tables, when it is coming like that, that is also correct. So otherwise, let us see. This you can solve by what we can solve? W23 equal to, yeah, W23. How can you solve this?
So W23 equals to Q23 here.
P2 V2 and then ln V3 by V2 is this. Can we use this also?
Yes, sir.
We can use this, right? Okay, so let me write in appropriate way. Okay, then this is P2 multiplying, but that is a V we need, but still here mass also let us multiply. That will be giving you volume. Yes. Then this is SP all 2. Yes. So multiplying LM. Okay. And then SP wall 3 by 2. Now we can delete this. 3 by. So let us see here. Let us see here what it will be reflecting. Okay. So Q23. Q23. This is right. It is giving you 152 in that case. Okay, that difference anyhow. The slight difference was there, that is taking from properties and all. Okay, so let us ignore those all. Even here we have not considered any Q value also. We are not using this particular thing. We are just calculating our work from our formula PV multiplying ln V3 by V2. Okay, that way your work is coming like this. Okay, let us follow this. Let us follow this. Maybe that example what they have considered, we are just following this example and we are formulating like that. So this
But
also
sir,
we can use.
but sir, in that case, the first law will be violated, na? That
Yeah,
Q.
this I agree. This I agree, but still, yeah. So this is.
So, sir, if in the exam or any time the question will be asked, then what should we
Okay, let
follow?
us check.
The
Yeah,
table or the first law?
let me check. Let me check, and then I'll write to you. Okay, I'll post that in our discussion only. Okay, what the present author have been considered. Okay, so that let us see. This is the textbook solved problem only. Okay, let me check and let me come back to you. Okay, but anyhow, we will not use this particular thing. Let us use this thing. You know anyhow very well about this. Okay,
But
V1
in
V1.
normal, but sir, in normal case, the first law will be satisfied in any question, na? Like there will be no such that disparity in caution like here we saw.
Uh-huh. Yeah, let maybe see in these problems actually there are a few mistakes also here and there. Okay, so that could be like that. Let me check. Otherwise, we cannot blame the textbook also. Let me check and let me come back to you after this class. By evening itself, I'll write you in the portal. Okay. So now let us go through this. We are considering this anyhow. So P2 V2 ln V3 by V2. Okay, that way we have calculated our work. We are not depending upon this particular thing. Okay, very fine. Thank you. Okay, now what we need to do? W13. Yeah, W13 is what? So that is P3 V1 minus V3. Is it? And also since V's are here specific volumes, we need to multiply with mass also. Okay, then multiply SP whole. Yeah. So then what is this W13 giving? W13 giving minus 124. Here what we got? W13, yeah, minus 125. Okay. Anyhow, W12 is 0. So W of the cycle equal to W23 plus W13. Yes. So So what is this network? It is 27.47. So that is positive. So we can write like, since the work is positive, okay, the cycle is okay. That is it. Yeah. So this is the procedure we have followed. Regarding that, let me check and come back to you. These properties table are changing something, or what is the textbook has written. Okay, I'll go back and check and then let us come. Okay. So this is about our code we have written. Let me copy. Okay, and let me put upon. Yes. Okay, and then this is the Word document I am sharing with you now. Whatever the codes we have written. Okay, so this is the document with all problems code whatever we have written like this way. Okay, this all the codes are pasted in that Word document and I have shared with you. You can practice it by yourself. Okay, once you practice these all, even new problems also you can practice very well by yourself. And even I have given one link over here. You can see it. Okay, through that link also. Yeah, this link. Where is this? Yeah, you can download. Okay, R1 folder I have pasted over here. Okay, ES folder. With this also you can install it, and then practice. Okay, this is fine. This is about ES. Okay, this is very simple. Only thing is practice is required, nothing more. So let's go back to our next chapter. Is it fine, or do you have any doubts? Can I go to next chapter?
Yes, sir.
Yes, sir.
Yeah, I'm coming. Okay, so far what we have seen. So some introduction topics. Okay, then after zeroth law of thermodynamics, then first law of thermodynamics. Okay, then properties of pure substances, then respectively the tutorials for first law of thermodynamics as well as properties of pure substances we have solved, and so far we have seen how to solve the problems in ES also. Okay, and respective materials also we have shared. Okay, that is fine. So let's move to the next chapter, that is about applying first law analysis to the control volume. Okay, so then here we are calculating our continuity equation and energy equation we are solving over here. Okay, you know what is the control volume. Okay, control volume means open system. Yes, open system. The closed system means what? The mass will be closed in that. Okay, the mass transfer will not be happening. Okay, however, the boundary would be changing. Okay, that means the closed system can contract or expand. Okay, then respectively heat and work transfer can happen. That is the closed system. Yes, in case of the open system, since the name itself is saying it is open, okay, mass transfer would be there, means mass crossing the boundaries as well as energy and work. both will be crossing the boundaries. Okay, so these all are our regular problems. Okay, practical problems, whatever we are seeing. So for this thing, we are developing our equations. Okay, continuity equation means conservation of mass equation and energy equation. So as you know, this is your control volume. This is very small topic actually. Okay, thermodynamic actually topic wise these are small, but only thing is many parameters involved. Each parameter is interlinking to each other. Okay, other parameters. So that way, if data is given two parameters, then rest of four parameters you have to calculate by following certain relations. Okay. Then with that you have to work with what is the heat transfer, what is the work transfer. Okay. This is actually conceptualized understanding and practicing. Okay. Once you practice very well with these all problems as well as with all equations, okay, then you will be strong in case of thermodynamics. Okay. So like that, this is one small topic we can cover in this class itself. And next class, let us go to the tutorials on this problem. Okay. So this is the control volume. Here, mass inlet is happening and mass exit also happening. Okay. Simultaneously, this is also the conceptualization of the control volume. Mass inlet is there, mass exit is there. Okay. Simultaneously, heat transfer is happening. Simultaneously, work output is also happening. Can you give one best example for this? Anyone? So we have explained you certain things in our previous introduction classes itself, in some other places. Can anyone give one example for this? Wherever mass is entering and mass is leaving, simultaneously heat transfer is happening. Okay, simultaneously work is coming out. Okay, or otherwise,
Jet engine.
pardon?
Jet engine where we take some mass and the
Okay,
energy will
so
exhaust.
when that is a scenario like when you are considering total engine itself as the control volume. Yes, sir. That time we have to consider instead of particular components, you have to consider total system, means total engine as your area of study or control volume. Yeah, exactly. Exactly. As like here, any system, as like jet engine, whatever air is taking by the propel means compressor, okay, and that is passing to the combustor. In the combustor, heat addition is there. Yes, sir. Through that you are getting work output as well as work output through the turbine. Okay. Also you are getting some other work output in case of jet engine, that is generating by thrust in the nozzle. Yes, sir. And then here whatever the nozzle is exiting, right, that mass itself is coming out. Okay, like this any system, even all the operating systems whatever you are getting, those all systems are like this. Okay, so here what we can call, this is the control surface, we can call this is the control volume total. Whatever the surface outside is there, that we can call it as control surface. Okay, so in this control volume or open system, the mass, heat, work, okay, as you are seeing over here, these will be crossing the control surface. Okay, like all the devices, if you see here examples are given. Turbine itself you can take. In the turbine, what is happening, if you take it as the turbine, so which turbine? Any turbine. If it is the steam turbine, okay, so from the boiler, superheated steam is coming over here. Okay, that is expanding. Okay, expanding in the turbine blades. Because of that, you are getting work over here. Okay, that steam, saturated steam or slight moisturized steam is leaving to the condenser in case of steam turbines. Yeah, in case of gas turbines, hot combustion products from the combustion chamber coming over here. Yes, those all are expanding in the turbine blades. Because of that, pressure energy is converting to the kinetic energy in the blades. Okay, that is developing the work. Okay, that work is coming out. Those anyhow, these hot products, okay, are going further to the nozzle, which is developing thrust. Okay, like this, whatever here we have over here, all the things in certain way you have to analyze. Okay, then all the systems like turbines, compressors. Okay, compressors means that is a reverse phenomena. Mass is coming here, that is getting compressed and going to the other operating system or otherwise in the storage tank in case of normal compressor system, or in case of your gas turbine engine, low pressure gas is coming, it is compressing and going to the combustion chamber. Is it? So there actually instead of work output, it is work input. Okay. This anyhow sign conversion will be changing. Okay. Their work input and nozzles. Okay. And diffusers and pumps. Pumps as like your compressors only. Okay. And heat exchangers, reactors. These are all the things. These all are process applications. Okay, fluid is going over here. With that fluid, whether we will be getting the work output or we will be supplying the work upon that. Okay, like that. These all are the applications applying over here. Now, so what you are studying over here, that is like by using this control volume concept, we are solving as we have initially assumed conservation of mass equation we are developing and conservation of energy principle also we are developing. Okay, and also same time few things are like steady state condition, few things are like transient condition. Transient condition means with respect to the time mass is changing. Okay, steady state means with respect to the time mass is not changing within the domain. Okay, so can you give some example? So steady state means if you consider the turbine, okay, so since continuously hot gas or otherwise superheated steam is coming in, okay, and low pressure steam or low pressure hot gas is leaving the turbine. Respectively, work we are getting output. This is the continuous process. Once you assume that the power plant or otherwise gas turbine engine operating for constant thermal input. Constant thermal input means constant heat supply. Okay, so that time the mass will not be changing within the control volume. The next one is what? Transient case. What is the transient case? So let us assume you have one tank of water. Okay, at t equal to 0, what is happening? So let us assume even though the tank also one inlet is there, one outlet is there. Okay. Let us assume inlet diameter, inlet mass flow is certain, outlet mass flow is certain, both are same. Okay. At a time equal to 0, let us assume even in the tank also certain amount of water is maintaining. Since inlet quantity is same and outlet quantity is same, the level will not be changing in the tank. Okay, that is simple phenomena. Okay. Now the outlet, okay, the outlet quantity is increased by opening the wall or otherwise by making another hole. Then what will happen? Inlet is same, okay, since outlet is increased, volume in the tank is slowly reducing. Yes, yeah. Otherwise, one tank is there, the tank is with the compressed, fully compressed air. Okay, then what will happen when you open the wall? Since no supply, then obviously the mass in the tank will be with respect to the time varying. Okay, or otherwise your cycle time or bike tire or car tire. Okay, so at time equal to 0, that is at certain bar of pressure. Okay, open the wall and leave it. What will happen? The air is escaping. Okay, these all are coming under transient condition. Okay, also in case of the internal combustion engine, yes, in case of internal combustion engine, during intake, when inlet valve is opened, when piston is moving down, suction is creating, okay, then mass is continuously entering over there. Okay, anyhow the boundary is also moving. Okay, in the same time, in case of internal combustion itself, engine itself, even in the exhaust stroke, after the power stroke, what is happening? Exhaust stroke will be coming. That time outlet port will be open, the piston will be moving up. Okay, whatever burnt gases are there, those burnt gases are pushing out. Okay, that time also even control volume. Okay, that boundary is moving. Okay, but whatever, irrespective of that boundary moving and all, if you consider that itself is the volume, okay, your control volume, then mass is reducing. These all are coming like transient state cases. That means within the control volume domain, certain mass is changing with respect to the time. Okay. Now, these two equations of conservation of mass as well as conservation of energy, we are deriving for these two cases, since these two are our regular applications. Okay. So this is, so here what is happening? This mass is entering over here. This is the control volume. Okay. Then it is leaving over here. Since here we are not talking at present whether it is the steady state or otherwise transient state. Okay. We are just step by step we are understanding. Okay. So whatever mass storing over here within the control volume is net rate of inlet minus net rate of outlet. Okay. Time rate of flow of the mass in across inlet A. Okay, whatever the mass is coming in and whatever mass is going out. Okay, so at a time equal to 0, suppose this is the empty, then what will happen first? This mass will be accumulating over here, then simultaneously leaving as well as accumulating. Yes, okay, so like that. After once it is reaching to the full condition, means mass is properly accumulated, then after it will be leaving. Okay, so like that, whatever it is, charge contained within the control volume equal to whatever inlet minus whatever exit that we have taken. Okay, and here it is not necessarily one inlet, one outlet. It could be many inlets, many outlets. Okay, suppose simply take one tank, water tank, two pumps are supplying. Okay, but exit is only one, or otherwise only one pump is supplying to the overhead tank. Okay, but many people are drawing, means many flats are there in particular apartment. Okay, many people are drawing the water. Yes, many outlets. Okay, in that case one inlet, many outlet. That means inlets and outlets could be any number. So to accommodate this number of inlets, number of outlets also, so this sum, okay, we have used over here, sum of all inlets minus sum of all outlets. This is the control volume, change of the mass with respect to the time within the control volume. Okay. Okay. The same like that individually, like this case what is happening, this case what is happening, this case what is happening, we are summarizing over here. At time equal to t, this is the amount of mass inlet plus the amount of mass in the control volume at t. Okay, at time equal to t plus delta t, okay, mass leaving is amount of mass leaving. Here, this is the mass within the tank. Okay, at that particular time. Okay, so then conservation of the mass principle. Okay, so whatever mass is coming, that is leaving after certain time. Okay, after this case. Okay, so mass cannot be created, mass cannot be destroyed, right? Conservation of the mass, both we are equalizing. Okay, then these two parameters, okay, we have equalized. Okay, and then we have solved like this. This we can consider it as conservation of mass. Okay, so but this is for whatever this we are doing for open system. Yet initially we have mentioned it, open system, that is your control volume. If it is a closed system, you read this particular sentence. Okay, closed system, if it is always constant, because mass is not exchanging from the system to the surrounding. Okay, probably energy and work may be interacting. Okay, so this control volume is open system. Then those equations actually we have changed like this. Okay, and then we are considering this limit t equal to means approaching to 0. Okay, then this is actually irrespective of whether it is a steady state or transient, but finally equation we have derived like this. Okay. Then this is the another way, like with the integral application. Okay, whatever mass entering, this is a very basic phenomena you might have seen in case of your class 12 mathematics also. Integral, this is the density, okay, and this is the volume simply. Okay, this is the density multiplying by volume. But however, here, if this is the supplying channel, okay, this is the cross-sectional area we are taking. Okay, that is dA, and this Vn, okay, this is normal velocity we are taking it over here. Okay, so to the control domain, as like this control domain. That integration we have applied over here. The similar way, okay, if we have this kind of any application like that, whatever it is entering, whatever it is leaving, okay. So in terms of that, so we have derived this of your conservation equation. Mass of conservation equation is very simple. Okay. So what is the steady state? Steady state means rate of change of mass with respect to the time equal to 0. Okay. That means the vessel level is all the time same. Whatever inlet is coming, the same amount is leaving. Okay. Whatever inlet is coming, the same amount is leaving. Yes, like suppose if you take only gas turbine combustor or steam power plant burner, okay, what is coming in case of gas turbine combustor? Air coming from the compressor, okay, the fuel continuously injecting from your fuel nozzle, okay, mass 1, here multiple masses are there, yes, mass 1 is your air, okay, mass 2 is your fuel, okay, then combustion reaction taking place. Now what is the exit mass? This mass 1 of air plus mass 2 of the fuel. Okay, these are hot gases. Since combustion reaction has been taken place over there, whatever the fuel has the chemical energy, that chemical energy has converted into the heat energy. Yes, sir. So because of the heat energy, this total mass is at certain high temperature and high pressure. Okay, then this hot gases anyhow going to the turbine. Okay, whatever this combustor itself, if you consider your control volume, mass 1, mass 2 inlets are there, mass 3 is the exit. Okay, so however, when you are running this particular combustor at constant thermal input, okay, then these inlets are same and outlets are going, the reaction is happening. No change in case of mass accumulation inside the combustor. Okay, that is inside the combustor means that itself is your area of domain, which is your control volume. Is it? That is your control volume. Okay, that case we can consider it as a steady state equation. Okay, this is whatever this equation we have derived over here. Okay, this equation in terms of integral form we have substituted over here. Otherwise, nothing. Okay. This is a rate of mass accumulation inside your control volume. Okay. This is in altogether inlets. This is altogether exits. Okay. In terms of the integral function, we have substituted it. So this is one example. Okay. This example actually we no need to practice over here. So some construction work is going on over here that is making some noise. So please bear with me for a few minutes. Okay. So this example anyhow it is there in your slides itself. Once I share these slides, Okay, you can go through it. Okay. So then this is simple, nothing more actually. Mass 1, mass 2 are coming, mass 1, mass 2 with different temperatures and pressures. Okay, and then mass 3 is going out. Okay, so that what are the velocities and all you will be seeing over here. We are considering it as the steady state. Okay, we are considering it steady state. Whatever is both are coming in, those are leaving as the out. No accumulation inside. Okay, that means it is the steady state. Then this will be 0. Then M1 plus M2 equal to M3 obviously. Yes. Yeah, this is. Yeah. Then respective things, whatever the uh, amount of magnitudes are given, according to that we are calculating velocity. This is a very simple problem, no need to discuss. Anyhow, it is there in the slides, you can see that. Okay. Now, what we have seen, we have solved conservation equation. Okay, so mass of accumulation inside the control volume equal to mass altogether inlet minus all the mass outlets. Okay, that we have taken. If dm by dt of control volume equal to 0 means that was the steady state. Okay, in that case, all mass inlets equal to all mass outlets, that we have derived in our previous case. Okay, so that is conservation of mass equation. Now, energy equation. This is very important actually. This is energy equation. So if you see here, this is our control volume. Okay. With this control volume, certain fluid is coming over here. Yes. And certain fluid is leaving over here. Those might be having this particular fluid itself is at certain high temperature. Yes. Because of that, that internal energy is different. Yes. Whatever here we are leaving, that could be at low temperature. Okay, their internal energy may be low. Okay, so that is only in case of turbine, whatever it is happening. Yes, so that is the reason some amount of work coming out or some amount of heat transfer taking place. Okay, okay, and also whatever coming in that has certain high velocity. Okay, whatever is leaving maybe that has certain low velocity. Okay, like this, whatever is coming in, that is delta E, delta capital E. When we are deriving that time, okay, first law of thermodynamics, delta capital E equal to Q minus W we have seen over there. In delta capital E, what all are included? Internal energy and kinetic energy and potential energy. Okay. Anyhow, in these most of the systems of thermodynamic systems, many times we have mentioned that most of the systems we are neglecting this kinetic energy as well as potential energy. Okay, we are talking in terms of internal energy, work, okay, and heat. Is it? That is this. Okay. So now let us see. Time rate of change of energy contained within the control volume at T. Okay. Net amount of energy storing in this particular domain is equal to net rate at which energy being transferred by the heat transfer. Okay. Like this. Suppose in case of gas turbine combustion, what is happening over there? Fuel injecting. Is it? That is heat addition to the control volume. Yes. So net rate of heat addition and the net rate at which energy is being transferred out. Okay. Here certain energy is going by. That could be through the work. Otherwise, it could be through other source of heat losses like Q only. Okay. Or otherwise, not necessary to be only work. It could be work plus Q also. Okay, that is this. But anyhow, whatever that Qs are there, right? All the Qs together again coming in this Q section. Okay, that is a net rate of energy transfer to the control volume. Okay, that means the amount of energy within this material is transferred. Okay, that let us see. So like this. This is the control volume, rate of change of energy within that. This is the Q and this is the W. Okay, and this is delta E. capital delta E, this is combinedly this big term. Okay, but here it is mass flow rate of inlet, this is mass flow rate at outlet. Okay, the internal energy, this is kinetic energy, and this is potential energy. Okay, and also over here, with respect to the time, once you talk, then we can take it as steady state as well as transient state. Let us see. Okay, so along with that, okay, so there is a certain work also. Work is actually two contributions. Okay, some work is like because shaft work or otherwise mechanical work we can call. Okay, the certain other work is like work developed or induced by the fluid force. Okay? That is by fluid force. That is simply impinging upon certain things of high pressure gas or otherwise high pressure fluid. Okay, that's what it has certain pressure. Okay, and it is impinging upon certain area. That's what this is the force. Okay, and multiplying by the velocity. Yes, that is giving you work. These works also involved over here like this. The work is control volume work. Okay, and then the fluid power, whatever it is coming in, this is, and whatever it is, the work in terms of fluid power leaving out. Okay, so these things also we are considering. The whatever work generating by this thrust. Okay, so this we can call it as flow work. Okay. So these are equations actually you have to practice. Once you use them in your example problems, okay, so then you will be able to understand very well. Now, this is, we have included over here your flow work also. Along with that, your flow work, PV. Okay, obviously in thermodynamics, what we have seen, pressure multiplying by volume is below that curve, whatever is coming out, that is the work. Is that? So, integral PV. Yeah, the integration limits V1 to V2. Okay, that itself we have derived. Work for constant volume, work for constant temperature, even many polytropic processes, constant pressure processes. Yes, sir. So that we have derived, right? That is our the flow work, whatever. That term also added over here. Okay. Now these two terms combined. Okay, U plus PV. What we have called over there, we have derived one term. Okay, we have identified one term that we call enthalpy, U plus PV. Okay, so for these two terms, we have included over here enthalpy. Okay, this is your energy equation. This total thing is your energy equation. Okay, you should remember. Anyhow, kinetic energy, potential energy terms we will be neglecting. Okay, that time rest of things are like your whatever this energy equation. So again, in terms of the integral form, okay. So these all are based upon inlets, okay. Whatever we have considered, integral form in terms of that also. So here masses are there, okay. Here mass is there. The mass term is replaced by integral rho a v. Is it? Yeah. So those we have included over here, okay. So we have changed our equation in terms of that. Otherwise, nothing. No need to worry by seeing this much of big equation. Okay. So read this presentation after that, step by step. Okay. So by reading the text, you can understand very easily. Okay. Nothing is there in this big equation. Okay. Now, this is like, here we are considering steady state. What is the steady state? This is accumulation, whatever is there, that we are equalizing to 0. Okay. That we are equalizing to 0. Okay, that means change in the energy within the domain. Okay, that is 0 here. That is this in case of your conservation equation. In case of energy equation, we are considering it as control volume energy change equal to 0. Okay, that's what whatever in our previous equation. Okay, this term or this term. Okay, this term we are equalizing to 0 when it is steady state. Okay. That is this, and rest of things are here only. Okay, rest of things are here only. This is, in that case, this is the energy in, this is energy out. Okay, this is again same. So when we are considering over here, mass inlet 1, mass inlet, mass outlet, both are same. Okay. And then we are considering this equation. So this is about steady state. Okay, but no case is steady state exactly. Okay, so if the fluctuations are very less, okay, and then we are considering certain average. Okay, pressure fluctuations will be there. If pressure fluctuations are there, then obviously mass fluctuations will be there, energy fluctuations also will be there. Even in case of certain combustion applications, pressure fluctuations are dominating upon energy release also. Okay. If energy release is varying with respect to the time, these perturbations are coming in. Okay. In that case, what will happen? So you cannot assume your system is steady state. Okay. But however, our systems, whatever, all the systems, whatever we are considering, okay, in thermodynamics, we are considering it as a steady state. Okay, for our convenience. Okay. So, so in that case, actually, by minimizing these fluctuations and we are considering certain average, okay, we are considering it as steady state approximation. That is approximation. So now your energy equation, whatever we have, okay, this energy equation, this thing suppose, okay, we are applying to different components, okay, like all these components, whatever in the example we have seen, right? We have mentioned that turbine, yeah, compressor, okay, nozzle, yes. So these are all the things we are checking over here. Okay. So this is the nozzle. This is convergent nozzle. This is divergent nozzle. Okay. In this case, we can call it as the nozzle. Here we can call it as a diffuser. Okay. What is happening over here? Here actually high pressure fluid is coming. Okay. That pressure energy is converting to the kinetic energy over here. Okay. In case of diffuser, is the reverse phenomenon. Okay. So pressure is increasing over here. Okay. So here, whatever it is happening, no mechanical work, only fluid properties are changing. Okay. Certain fluid properties are changing, but however, no mechanical work is happening over here. That is the reason in our equation, okay, in our equation, this term we are considering it as 0. Okay. This term we are considering it as 0. As we have assumed, all the systems we are considering here as steady state systems. Okay. That is the reason this term itself is already 0. Yes. This term itself is already 0 in this equation. This equation that is already 0. And here what we are considering it is also 0. Okay. And potential energy. Okay, potential energy is actually if there is suppose 100 meters difference, okay, 500 meters difference, height is there. In that case, whatever the kinetic energy, when you compare this potential energy with respect to the kinetic energy, okay, at higher altitude differences, that meaning would be there. Okay, suppose see, in case of your hydropower plant, what is happening? The water coming from penstocks. Okay, you might have seen in our fluid mechanics. Okay, and those high velocity water from the penstocks, whatever is higher altitudes, those having kinetic energy as well as potential energy. Those are impinging upon our Pelton wheel turbine. Okay, or otherwise reaction turbines like Kaplan turbine or Francis turbine. Okay, so that way you are taking energy. Means kinetic energy converting to the mechanical energy, then mechanical energy obviously converting to the electrical energy when you are running in your generator. Okay. Here, in case of any steam power plant, suppose, okay, there are nozzles which are impinging upon the turbine, right? So those nozzles actually inlet of the nozzle, outlet of the nozzle. There is no much difference. The nozzle is there only, that itself is very small component. Okay. In that case, actually, you no need to worry about, or you no need to consider about this particular potential energy. In that case, this term gone zero because there is no work output in case of your nozzle. Yes. So that is the reason heat term is there. Okay. And the enthalpy term is there and the velocity term is there. However, the heat term also, if you consider again, it is the adiabatic. Okay. That means heat transfer to the surrounding is zero. Okay. In that assumption also, you can make it is zero. Okay. Then here the velocity at V2 in case of the nozzle is function of V1 and enthalpy change. Okay. So like that, we will be that equation, whatever the main energy equation is there, right? This main energy equation, we are converting to every application over here. Okay. Now same like that way. And 1 minute, this slide has gone down. Okay. So here, in case of turbine, okay, this could be any turbine. What is happening over here? The fluid is coming like this and fluid is leaving like this. Okay. This is high enthalpy fluid in case of steam turbine. Okay. Or gas turbine, high enthalpy fluid. Okay. Then here enthalpy loss is happening over there because it is expanding on the turbine blades. Okay. So this enthalpy loss itself is converting as our work. Okay. And then here low enthalpy fluid is coming. Okay. In this case over here, no matter about your kinetic energy, okay, no matter about your potential energy, okay, in case of steam power plant or otherwise these kind of axial flow turbines, okay, and that is the reason here we are not considering your kinetic energy as well as the potential energy, but however heat involved because the high enthalpy fluid is coming here, yes, the heat terms are involved over here and the enthalpy terms are involved over here. We are getting work over here, is it? We are getting work over here. That's what work term also included over here. Okay, so like that, and even different applications like this is compressors and pumps. Okay, so these are like different pumps. Like this is a reciprocating compressor. We can call it as. Okay, this is a rotary compressor. Okay, this is centrifugal compressor. Okay, this is vane compressor. Okay, this is like the screw compressors. Many compressors are there over here like this. Okay. In that case also, we are considering like this. This is only taking work. Okay, heat transfer terms nothing. Q terms are nothing. Okay, it is taking work actually. Okay, so work input is there. Work done upon the system is there. Okay, work done upon the system is there. So like that we are reducing our equations. So here in case of your heat exchanger, okay, so considering the domain is most important over here. Suppose heat exchanger means actually this is nothing. It is exchanging the heat from hot fluid to the cold fluid. Okay, as like suppose you have one hot means one glass of hot milk. Okay, this is time to go somewhere. Okay, you don't have much time. Then what would you do? You take that hot glass of milk and then putting in big vessel of water, okay, and then yourself you will be moving here and there slowly, okay, without spilling the milk in the water. Then what is happening over there? Your water and milk both are not getting mixed, means mass mixing is not happening. Only high heat means high enthalpy or heat from your milk is transferring to the water in the big container, is it? So that is only heat transfer. What is happening over there? Heat exchange is happening. As like that, this is one equipment or instrument we can call. Yeah, class is going on up to 11 o'clock. You can come up to 11. Yeah. I'm sorry. In between somebody came. Okay. So as like heat transfer means heat exchanger means we will be using in many applications as like all thermal power plants. Okay. So everywhere it is there. Okay. All chemical industries. Okay. So everywhere heat exchangers are there. Here this is one fluid, this is another fluid. Okay. As like the example like your hot glass of hot milk and water in the vessel. Okay, same like that. Here masses are not mixing, but because of the metal to metal interaction of both the fluids, okay, so high temperature to low temperature, the energy transfer is happening, heat exchange. Okay, in that applications also, no work involved over here. Yes, sir. No work involved over here. That's what work terms are zero. Okay, so like that we are considering different equations over here. Yes, and in our thermodynamics, we have very important process that is like throttling process. Okay, throttling process. So in case of in the first class when we have analyzed or studied about refrigeration cycle, okay, there we have explained one valve is there actually. There actually, if you see over there, mechanical kind of valve is given over there. Okay, so we are here only. Why not we open that? This is right. Do you able to see this slide? I have changed the slide. Can anyone please confirm me?
Yes, sir. Yes, sir.
Okay. See, this is your refrigeration cycle. I don't have control on my mouse. I don't know, surprisingly. What is happening? My mouse point is not coming. Yeah. Now I have set me. Yeah. See here. So here, in case of your refrigeration system, okay, let us come from this point. Here, this is vapor actually. Why it is vapor over here? So here, your refrigerant has absorbed the heat from your the food stuff in the refrigerator or otherwise in the room, okay, where we are staying in the room, okay, that heat also absorbed by your refrigerant, and this refrigerant got evaporated in case of this evaporator. So this is in case of your windows, not window, this split AC, whatever the indoor unit is there, right? That is this component. Okay, that is this component. Rest of these three are in our outdoor unit. Okay, rest of these three are in our outdoor unit. Okay. Here in our indoor unit, when it is absorbing heat from the room, the liquid refrigerant is becoming vapor. This vapor is going to the compressor. Okay, it is compressing. Okay, then here it is condensing. This is the condenser. Okay, here it is changing its phase to the liquid. Okay, and here we have one valve actually. This is throttle valve we can call. In case of your refrigerator also, backside you can see very thin long tube like a coil. Okay, that is your throttle valve. What is happening when it is going over here? Because of the throttling process, okay, high pressure to low pressure sudden expansion, okay, the fluid is becoming cold, okay, the temperature of the fluid is further reducing over here. Okay, that is purpose of this. Okay. So here we are using, that is the reason this particular application. Yeah. Okay. So this is the inlet and this is the exit. A narrow passage is there over here. Okay, a narrow passage is there. Because of that, it is even there we have seen in thermodynamics also free expansion. I have explained you. Yes, similar concept like free expansion. Okay, here heat transfer or otherwise work transfer, both are zero. Okay, the only the fluid is getting cold. Is it? Fluid is getting cold. Enthalpy variations are coming. That's what enthalpies are involved over here. Okay, and here since this is the narrow passage over here, okay, pressure drop is happening over here. Okay, here high pressure, here low pressure. Okay, so because of that, velocity here is increasing. Okay, so that's what these terms also may be, but that is anyhow. Here, what in this case of this is the porous plug. Okay, maybe that velocity gradients are there over here. After going a little downstream direction, that velocity is also coming into the normal. Okay, that's what even enthalpy variations. So this equation we have considered like this. These equations we are deriving to the particular application oriented. You can read very well, then you can understand. One class is not sufficient to understand this. The thermodynamics is actually you have to increase interaction with that. Okay, you have to read slowly as like a story. Then it would be very nice subject for you. Okay. Now the thing is, whatever the rest of our thing is like so far what we have assumed everywhere over here, we are assuming everywhere over here dm by dt equal to de by dt equal to 0. Okay, why are we assuming over here? We have considered it as steady state. Is it? We have considered it as steady state. Now we have to see these all the things for transient analysis. Yes. Nothing transient analysis. This part is also coming in the picture. Okay. This will be there. It will not be equalized to 0. Then time functions are coming in the picture. Then you have to integrate with respect to the time. But we are not studying very much about this. Okay. We are just knowing how it behaves. Otherwise, nothing. Okay. And even this is your energy balance equation. This term will be still existing. Okay. This will not be getting to 0. Then once you integrate along with that equations, okay, and then how it is changing, these all are explaining over here. Okay. These all are simple mathematics terms only, otherwise no relation with thermodynamics and all. Okay. So this is about applying first law of thermodynamics, okay, to the control volume. Okay. This is about that. In next class, let us solve some problems. Okay, then you will be able to understand very easily. So that is about this. After this class, I'll be sharing this presentation with you. Okay, I think codes I have already shared for those 7 problems. Okay, you please practice it. Okay, thank you. Thanks a lot. So any doubts? Do you have any doubts regarding this? Okay, if you still have any doubts, then you can write over there in the discussion forum. Okay, then I'll be responding to you. Okay. Okay, thank you.
Thank you, sir.
Thank you, sir.